In this particular lecture, we are going to discuss about the cascade loop and how the cascade loop is represented in the P&ID. We'll be taking an industrial example and show you how this is really done in the industry. We'll be taking an example of a level flow loop and another temperature flow loop and explain you in detail how the cascade control really works and how it is really shown in the P&ID. Let's begin. So take this example. We discussed with these examples for the BPC's control system. So I think I have taken the same example so that it becomes easy to you for understanding. So this is the inlet, right? And this is basically the outlet, right? And the maintaining level of this vessel is important because you don't want overspill because of the safety reason, and also the level should not go very low because that may cause the downstream equipments to malfunction. Like if there is a pump at the downstream of the valve and the level goes very low, the pump may get damaged due to the dry run. Okay, so that is the reason why our level should be maintained. How the level is measured? The level is measured through an LT. So LT provides you PV, and this LIC is getting set point from the operator, and it generates basically MB. So in the ideal case, what will happen is out in the normal, not ideal, I would say in the normal BPCS case, what will happen is signal from this LIC will directly go to the valve and the control will be done. This will be MB. So whenever level increases or decreases accordingly PB changes and the MB will change and that will control this valve, right? And that is how a simple process control works, and that's what quite fine in the most of the cases, right? But what happens in this kind of a control if there is a large variation in the downstream process? So in the downstream, there may be another valve, right? There may be a on-off valve, and there may be some other processes, right? So suddenly, if there is something that causes this valve to close, right? Somebody closes this valve because of the downstream reason, then what will happen? So the label, even if the controller is opening the valve or closing the valve based on this level, due to the sudden closure of the valves, the outlet flow will get stopped, and this will cause the label to increase. But this will take some time, and by the time the level gets high and your level transmitter responds and all the things happens, maybe the time is not sufficient to control the overspill, right? Because you see, every time the process there is a change in set point or there is some disturbance, the process does not immediately go to its set point. It goes through this cycle, right? And there is overshoot and undershoot also happens, right? So this, so process stabilization takes time. So that's why uh, the process designers or process controllers they thought that why not measure the thing that gets impacted first. So here in this particular example, when this valve gets closed, what get impacted first? What first senses that the valve is getting closed? It is the flow of this line, right? This flow of this line gets hit first. And after that, the level, building up the level and then the level transmitter measuring it will take some time, depending on how big the vessel is, how large the line is, and everything. But for any cases, for any size of the vessel, for any size of the pipe, it is a flow that will always get impacted first before the level. So that's why process designer thought, okay, let's install a flow meter here. This is a flow meter and sense the flow first. And let's have a flow controller and have a uh, have a closed loop with the flow itself, right? And instead of operator giving the set point to this FIC, let's output of the LIC, right, which is the MB, becomes the set point for this one. Okay, so let's have much more clarity. Okay, so if we can denote them by two different numbers. So first of all, this first controller or first LT, its output make it PV1. Set point is SP1 and this output is MB1. Okay, and it becomes the set point. So this becomes PV2, sorry, SP2, this becomes PV2 and this becomes MB2. Okay, so output of the first controller, that is MB1, becomes the set point of the second controller, right? So basically, we are trying to maintain the level, but we are doing it through the flow because flow is much more responsive to the downstream disturbances. If there is no disturbance, flow will remain the same and uh, there will not be much of an action this FIC will do. It will simply pass on this MB to SP2, right? Okay. And this is the way it is depicted in the P&ID also. You see there is a controller here. So this is the first controller here. And this is the second controller here or second control loop here. And between them, the link is a software link because this communication, this line, if you go back to our earlier lectures where we have discussed about what is the meaning of the different links, this particular links provides you a description of software link. So this is basically a software link. Let's erase them everything so that it becomes easy to understand. Okay. 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 Yeah. Okay. So this is the master controller and this is the slave controller. And this is the software link I was talking about. And this signals is the electrical signals. So if you are still confused about the symbols of different lines, so this is the electrical and this is the software signal, and normal line means it is a process line. So if you are still confused, you should go back to earlier lectures and see what is the significance of the different line. This particular symbol is of an orifice and this is a globe valve. And this particular LT is a diaphragm seal LT. This signifies the diaphragm and this particular line signifies the capillary. Okay, so hope this is clear to you. Now we'll be taking another loop. So this loop is our temperature loop. For this also we have discussed about um, the basic process control loop. So here there is a medium or there is a fluid which is getting cooled, right? It is getting cooled. For example, take this as a some hydrocarbon, okay? And it is getting cooled through a heat exchanger by the cooling water. Now the temperature of the outlet of the hydrocarbon is to be maintained because of the downstream process. How the temperature is sensed? Temperature is sensed through a TT. TT gives the signal as the form of PV to the temperature indicator controller. In the case of the basic process control system, there is a set point here, and this output actually goes directly to the valve, right? This was not there, this was not there. And simply when the temperature increases or decreases depending on that, this valve opens and closes, and this is how the temperature is maintained. But what happens if there is some restriction here or some valve here that gets closed, or the line gets choked, or something happens, right? Then the flow, this cooling water flow gets stopped or gets restricted, right? And this will increase the temperature of the fluid, but it will take some time. Maybe it can take 10 minutes of time to actually, uh, due to the loss of the cooling water, this fluid gets heated. And after 10 minutes, the temperature sensor understands it and sends the signal to the TIC, and then the action goes here, right? So it may be so late. In that situation, what is the parameter that gets impacted first? It is the flow. Again, your flow gets impacted first and much before your temperature, right? So that is why the process designer, what they do, they take this flow as a secondary loop to this master loop. So here it is the master and it is the slave loop, and they have this connection here. So output of this one becomes, so if it is PV1, SP1, MV1, this becomes SP2, this flow becomes PV2, and this becomes MV2, right? So now if there is a restriction or some obstruction or something happens in the downstream, the flow gets impacted very immediately, and immediately the controller can take actions without causing the temperature to overshoot or undershoot. This is how the cascade control temperature to flow loop works, and this is how it is depicted in the P&ID.